All right, let's talk about one of the coolest tools in data analysis, clustering. This is all about finding meaningful groups in your data, even when you have absolutely no idea what you're looking for. It's a powerful technique that's used pretty much everywhere, from marketing and finance all the way to medical research.
Right? That's the big question. It sounds like magic, but it's not. Today we're going to go under the hood and really explore the technical machinery that lets these algorithms discover hidden structures in super complex data. It's all about letting the data itself tell the story. So here's our game plan for this journey. First, we have to start with the absolute basics. How do we even teach a computer what similar means? Then, we'll crack open the k-means algorithm to see how it works. After that, we'll tackle the million-dollar question: how many clusters should we even look for? We'll also figure out how to see these groups in messy, high-dimensional data. And finally, the best part, how to turn these abstract clusters into real-world, actionable insights. Okay, first things first. Before we can even think about grouping anything, we need a solid, mathematical way to define what close or similar actually means to a machine. This isn't just a small detail, it's the entire foundation that everything else is built on.
You know, there are actually a bunch of ways to measure distance, but here are two of the most common. On the left, you've got Euclidean distance. Think of it as the crow flies, just a straight line from point A to point B. But on the right, there's Manhattan distance. This is more like how a taxi would get there in a city grid, moving along the axes. Which one you pick really matters, and it totally depends on what your data represents.
And here's where we hit our first major technical hurdle. This is a huge problem, because if you don't do anything about it, the algorithm will see the huge numbers for income and basically ignore the tiny numbers for wine bottles. The income variable will completely dominate the distance calculation, and your results will be totally skewed.
So how do we fix it? Well, the solution is to scale our data. And a classic way to do that is with z-score scaling. It sounds complicated, but the idea is simple. It basically rephrases every single data point in terms of how many standard deviations is this away from the average. This is brilliant because it puts all of your variables on a level playing field. Now every feature gets a fair say in the distance calculation.
And here you can see exactly what that does. Look at the original data up top. The income values are massive, totally dwarfing the wine spending. But check out the scaled data below. Suddenly, both variables are on a similar scale, hovering around 0. Now our algorithm can look at them both equally. Problem solved.
Okay, so now that we've figured out how to measure distance properly, we can finally look at the engine that actually creates the groups, the k-means algorithm.
K-means works in this really elegant repeating loop. First, it just takes a wild guess and randomly drops some cluster centers, we call them centroids, onto the data. Then, for step 2, it looks at every single data point and assigns it to whichever centroid is closest. And for step 3, it moves each centroid to the average spot of all the points that were just assigned to it. That's it. It just repeats those last 2 steps over and over and over again.
So how does it know when to stop? Well, it keeps going through that loop until the centroids barely move anymore between steps. At that point, the clusters have settled down, they're stable, and we can say the algorithm has converged. We've found our groups.
Now, we've seen how k-means works, but you might have noticed a catch. It relies on a huge assumption that we have to make up front. We have to tell it exactly how many clusters, that's the k, to find. So, how on earth do we pick the right number?
Well, one way to get a clue is to measure how tight the clusters are. And that's exactly what WCSS does. It basically adds up all the distances between each point and the center of its own cluster. So a lower WCSS is better. It means the points in each group are really huddled together, nice and compact.
So what we can do is run k-means a bunch of times. First say k equals 2, then 3, then 4, all the way up to 10. And we plot the WCSS for each run. What we're looking for is a bend in the graph, a point that looks like an elbow. That's the sweet spot. The point of diminishing returns, where adding yet another cluster doesn't really make the groups that much more compact.
But hey, having tight clusters is only half the battle. What if they're all tight, but they're all overlapping? We also need them to be far apart from each other. And this is where the silhouette score is so cool. It's a really clever metric that looks at both things at once: how compact the clusters are and how separated they are, all in a single score.
Think of it like a report card for your clustering job. A score close to +1, that's an A+. It tells you your clusters are dense and really distinct. A score near 0? Not so great.
That means your clusters are probably overlapping. And a negative score? That's a fail. It's a big red flag that some points might have been put in the completely wrong group.
Okay, this all works like a charm when we have 2 or 3 variables that we can easily plot on a chart. But let's be real, most interesting data is way more complex than that.
Exactly. You just can't. You can't draw a 50-dimensional graph. So we need some way to squish all of that information down into 2 or 3 dimensions that our human brains can actually look at. But, and this is absolutely crucial, we have to do it without losing the structure of the clusters we just found.
And for that, we have incredible tools like TSNE. Now that name is a mouthful, but think of it like a magic lens for your data. It's a really smart technique that takes high-dimensional data and flattens it down, all while working really hard to keep points that were close together in 50 dimensions close together on our 2D plot. It is designed specifically to make clusters pop out so you can see them.
Okay, deep breath, we've defined distance, we've run the algorithm, we've picked the best number of clusters, and we've even visualized them. But none of that means anything without this last step. Now we have to ask the most important question: what do these groups of data points actually mean? This is the payoff.
So to figure that out, we go back to our original unscaled data and we look at the average traits for each cluster. This lets us build a profile, kind of like a persona for each group. And suddenly we might see something like this. Ah, cluster 1, these are our high-income customers. And cluster 2, okay, these are the low-income, low spenders. This is the moment abstract math turns into real, understandable business strategy.
And this is why all that technical work matters so much. This final step is the bridge from data science back to the real world. Whether you're trying to create targeted marketing campaigns, identify different groups of patients, or spot fraud, profiling your clusters is what makes them useful, actionable, and ultimately really valuable.
At the end of the day, clustering isn't just a technical exercise. It's like getting a new pair of glasses that lets you see the hidden complexity in the world. It reveals these natural structures that were there all along. The real question is, once you find these hidden patterns, what are you going to do with that new insight?